Right. So good afternoon, good evening to all of you. So in the last class, I explained about the columns constructs. In the chapter, we discussed about how to calculate critical load for a column having different types of end conditions by using Euler's method. I have already told you what are the formulas for critical load for Euler's method. So, and I have already told you what are the assumptions we are going to take in Euler's method to calculate the critical load on a column having different end conditions. So today here I'm going to explain how to calculate critical load on a column by using Rankins method. By using a Rankins method. So all of you know it. So here I'm writing here the heading. This is columns and structs. So here by using the Euler's theory of column, we can find the what is the critical load on a column. That is by using the formula. So that is a PE is equal to, so that is pi square into E into I divided by L square. So this is the formula for critical load on a column. Both ends are hinged. Why? Because Euler's consider both ends are hinged is the reference column to find the all the equivalent length of the different columns having different end conditions. So by using this formula, we can calculate the what is the critical load on a column when both ends are hinged here. This is the hinged column. Both ends are hinged. It is also named as a reference column. So according to your Euler's theorem of column, right? So this according to Euler's theorem of column, Euler's theorem of column, we can find the critical load. We can find the critical load for different columns having different end conditions. We know that. So I will give simple what are the formulas of Euler's critical load for different end conditions of the column. So listen carefully here. So in this first case, both ends are hinged here. If the both ends are hinged here, what is the formula for critical load for Euler's column here? That is P is equal. It is also named as Euler's load or buckling load or critical load. We can name anyway. So that is equal to so pi square into E into I divided by how much L square. So in the second case, both ends are fixed here. So if the both ends are fixed here, then P is equal to that is 4 times of pi square into E into I divided by how much L square. And in the third case, one end is free, one end is fixed, other end is free here. Then we are applying the compressive load here. That critical load is equal to that is pi square into E into I divided by 4 times of L square. And the last condition we know very well. What is the condition here? That is one end is fixed, other end is hinged here. This is the fixed end and this one is nothing but hinged end. So what is the critical load according to Euler's formula? That is pi square into E into I divided by so L square into 2 times. So these are the formulas we can use. So these are the formulas we can use to calculate the critical load on a column when the column is subject to axial compressive load. These columns are having different types of end conditions. And at the same time, I told you already in the last class. So what is the slenderness ratio for any column here? So that is very important. So that always gives the limitation of Euler's theorem of column. So I will give simple explanation. After that, I will give the Rankins formula also. Okay. Right. So this is the slenderness ratio. So we know that this is nothing but a buckling load or bending load or a critical load or Euler's load. It is also named as bending load. I want to find the bending stress in a column. Bending stress is equal to bending load divided by area. Then I am writing here pi square into E into I divided by L square. But we know that K, radius of gyration, is equal to square root of I by A. Then squaring on both sides, then I am getting here K square is equal to I divided by A. Then I is equal to K square into A. So this is the formula for moment of inertia of a given cross section of the column, right? So I'm going to substitute this value in the above equation. Then I'm getting sigma b is equal to what is p here? That is pi square. That is, we can write here pe by area. Then we can write here into area also here. Then I'm writing here pi square into e. Into in place of I, I'm going to substitute k square into a. In place of I, am substituting divided by L square into A. Then here I'm writing area, both are cancel. I'm going to cancel it here. Then we are getting the formula. Bending stress is equal to, that is pi square into E divided by, I'm writing L by K whole square. I'm taking this K to the denominator, then I'm writing L by K whole square. Here L by K is nothing but slenderness ratio. So here I'm writing L by K is nothing but slenderness ratio. So this ratio always gives the limitation of Euler's theorem of column. Euler's theorem of column. I'll give simple example. What is the limitation of Euler's theorem of column? For example, I have already told in the last class, this theorem is always valid for long columns only. It is not suitable for short columns. So it is clarified by this centeredness ratio L by K. So please take care about this L by K ratio. So if you draw the graph between the bending stress and L by K ratio. So for example, if you take this is the column, standard column, both ends are hinged here. So if you apply the compressive load gradually, or if you increase the compressive load gradually, at a particular load it will undergoes bending like this. So at what load the column undergoes bending, that load is named as critical load, or that load is also named as buckling load or bending load or failure load also. Or you got my point or not? So when this column is under bending, at that point we are having bending load. That bending load is also named as Euler's load or critical load divided by area. We are getting the bending stress. So here, if you increase the further bend compressive load, this column bending more and more and more and more, after that it goes to crush. So if you take any column, we are having two types of stresses. One is nothing but bending stress, and another one is nothing but crushing stress, sigma C. But if you compare the sigma B and the sigma C, which value is the more value? Which value is the less value? At which value this column undergoes fail? So actually this compressive stress is always more than the bending stress, but failure occurs at the bending. So which stress we are going to consider in designing? So we are going to consider bending stress is the designing stress according to which theory? Euler's theorem of column. So here bending stress is always less than crushing stress. So it never exceeds the crushing stress value. If it exceeds the crushing stress value, then automatically, so this Euler's formula is not satisfied or not valid. I will give simple example. So listen carefully. How to identify this column is long column, this column is short column, and this formula is only suitable for long column. It is not suitable for short column. How can you say? How can you identify, and how can you clarify this difference between these 2 points? So between short column and long column. Okay, please take care about that one now. So for example, we are taking the mild steel. That is, I am taking the mild steel, Mi. So for mild steel, I am taking the Young modulus is equal to all of you know it, 2 into 10 to the power of 5 Newton per mm square. All of you know that. Or you got my point or not? And yield stress. the stress in the material, that is yield stress I am taking here, sigma y is equal to 300 newtons per mm square, for example, I am taking. So, so listen carefully. So maximum stress in the column is 300 Newton per mm square. If this is the limit of Euler's theorem of column, if you draw the graph between sigma b and I am taking the sigma b on y-axis. I am taking L by K is on x-axis. I got my point or not? I got my point, right? So this is the L by K ratio. This is 1, so 2, 3, 4, 5, 6, 7, 11, conduct 10, 20, 30, 40, 50, 60, we can take it. It is also 100, 200, 300, 400, 500, 600, 700, 800, 900, 1000 like this. We are writing 25, 50, and 75, 100, 125, 150, 175. We can take like this. Here is 100, 200, 300, 400, 500, 600, 700 like this. We can take it. So according to Euler's formula, so P is equal to how much? P by E. A is equal to sigma B, that is equal to pi square E divided by L by K whole square. So this is the formula. This is sigma B and this is L by K ratio. Now, when L by K ratio is goes on increases, then bending stress is goes on reduces. Bending stress goes on, it follows parabolic form. So why? Because we are having the square of the terms here. So it follows the parabolic form. So what is the maximum value here? So this value is nothing but, for example, this value is 300 Newton per mm square. This is nothing but yield stress or maximum bending stress in this material Mi. So corresponding to this point, if you draw the vertical line, it gives some value of 60, some value of 60 here. That is nothing but L by K ratio. L by K ratio is equal to 60. That is the limitation of Euler's formula. If this L by K ratio is less than 60, that is L by K ratio is less than 60, what happens? Less than 60 means it is reduces. It is less than, it is reduces. So when L by K is less than 60, then this sigma B or sigma by value is always exceeds this value 300. So that's why we are getting this point, this point, this point, this point. That's why this is the region in which the Euler's formula is satisfied. So this region is named as a limitation of Euler's theorem of column. So this region is always belongs to long column. It is not belongs to short column. So this is belongs to short column. But this formula is only valid for up to this region only, not for this region. So there is no formula for short column according to Euler. So this is the formula we can use to calculate critical load on a column. Uh, that column always belongs to long column. Okay, right. So this point is named as a limitation of Euler's theorem of column. So Euler's formula is satisfied in this region. Euler's formula does not satisfy in this region, not belongs to this region. Or you got my point or not? I hope you understood this one. What is the difference between long column and short column according to the Euler's formula? So Euler's formula is valid up to certain limit of L by K ratio. After that, Euler's formula is not valid. So this is clear to all of you. So for example, if you take this problem, for example, so I want to find the L by K ratio of this mild steel. Take these two values. I am taking PE value divided by area, that is equal to how much? Sigma B is equal to pi square into E divided by how much? L by K whole square. So sigma B is given, that is 300 Newton per mm square. So is equal to pi square into E divided by, so L by K ratio whole square. E is also given. Then I'm writing here L by K whole square is equal to pi square into E divided by 300. So E is also given, pi square into E is 2 into 10 to the power of 5 Newton per mm square divided by 300 Newton per mm square. These two units are cancelled. Then I'm writing and I'm finding the L by K ratio is square root of these values. That is pi square E divided by how much? 300. I got that value, that is 81.1 something, then we can say approximately 80. So this is the L by K ratio. That means L by K ratio is equal to 80, means that is the limitation of Euler's theorem of column. If this L by K ratio is less than 80, it is belongs to short column. The L by K ratio is greater than 80, it is belongs to long column. So according to this L by K ratio, we can easily classify which type of column it is. But I can apply this formula for only long column. This is not suitable for short column. Why? Because if the L by K ratio is less than 80, it always, this bending stress always crosses this maximum value, that is 300 Newton per meter square. So the Euler's formula is not valid within a certain region. It is valid within a certain region. That is named as limitation of Euler's theorem of column. Right. So this is the way of calculation of critical load according to Euler's formula. Euler's formula. So it is suitable for long column. It is not suitable for short column. But I want to use only one formula to calculate critical load on short column as well as on long column also. So that I'm going to use another method. That method is always, all of you know it, that is a Rankins method. That method is named as a Rankins method. According to a Rankins method, I'm writing here. I'm going to give it to you. What is the Rankins formula also? Right. Rankins formula. This formula is suitable for both short column and long column. So what Rankin says here, so when a column is subjected to a axial compressive load, there must be two types of stresses. One is said to be bending stress, one is said to be crushing stress. So we have two types of loads, that is column may goes fail under two ways, under bending, under crushing. So we are having two loads. One is said to be Euler's load or bending load. One is said to be crushing load. So at the same time, we are having bending stress and we are having crushing stress also. So we are having two types of stresses in the column when the column is subject to an axial compressive load. So according to Rankins formula, so here, according to Rankins formula, here I am writing 1 by P is equal to 1 by P plus 1 by PC. 1 by PC. Now tell me here, what is P here? P is nothing but Rankins load. Rankins load. And what is P here? P is nothing but Euler's load or buckling load. Euler's load or buckling load. And what is the PC here? PC is nothing but crushing load. PC is nothing but crushing load. So these are the terms contained in that equation, which is given by the Rankins. Now I'm going to apply this formula for long column and the short column. I can find the what is the critical load on these columns. So I want to find the critical load on the long column. I want to find the critical load on the short column by using the Rankins formula. Okay, so for example, if you take a long column, for a long column, for a long column, there are two loads are there. One is said to be P and one is said to be PC. That is nothing but Euler's bending load or crushing load. Now tell me, so between these two, which load is more than which load? So for long column, the column may fail at bending. It never fails at crushing. Are you get my point or not? So P is always less than PEC. P is always less than PC. So I am writing here according to when P is less than, that is PE is minimum. P is minimum. So PC is maximum. PC is maximum. Or you got my point or not? So if PC is maximum, P is minimum less than the PC, then automatically P is always less than the PC here. That is, buckling load is always less than the crushing load in case of long column. So according to your Rankins formula, I am writing 1 by P is equal to 1 by P 1 by PE plus 1 by PC. If P is minimum, if it is minimum, so what is 1 by P? Maximum. 1 by P is maximum. Are you got my point or not? So here PC is maximum. 1 by PC is minimum. So I'm writing here PC is maximum. Then 1 by PC is minimum. So I'm going to neglect this value in case of long column. I'm going to neglect this one. So then I'm writing here. So here that implies 1 by P is equal to 1 by P. This is the formula for Rankins for long column. So from this formula I can write directly Rankins load is equal to buckling load or Euler's load or critical load. So that is for long column. Okay. Now what about the short column here? If you take if you take a short column, if you take a short column, if you take a short column, so P is always greater than PC. That is, the short column always fails under crushing. It never fails under bending. So first of all, it fails under crushing. After that, it will goes to bending, but the bending never occurs in a short column. But in case of long column, first of all, the column undergoes bending. After that, it undergoes crushing. You will get two, but in case of short column, we can't see the bending, but I want to try to bend it, but it will goes to fail under crushing. Or you got my point or not? Right. So here, so when 1 by, so PE is maximum here, PE is maximum here, PC is minimum here. Now, according to Rankin's formula, if P is maximum, but what is 1 by P? That is always minimum I am writing here. So that implies when P is maximum, that implies 1 by P is minimum. So 1 PC is minimum. That implies 1 by PC is maximum. So I'm going to neglect 1 by P. Why? Because it is minimum. Why? Because it is minimum. So that I'm going to write that formula here for a short column. That is 1 by P is equal to 1 by P plus 1 by PC. I'm going to neglect it this term. Then I'm writing here 1 by P is equal to 1 by PC. That implies P is equal to how much PC. So this is named as crushing load. So by using this formula, I can apply this formula for long column. I can use this formula for short column. What is Euler's load here? So I am writing here Rankins load is equal to Euler's load. That is also is equal to pi square into E into I divided by L square for long column. That is clear already in the previous section. That is clear. But here for short column, how to use that formula? P is equal to PC. Or you got my point or not? So please take care about that one also. Okay. Right, listen carefully here. Listen carefully here. So here I am writing according to Rankin's formula for short column, then I am writing here P is equal to PC. P is equal to PC. Then I am writing this formula directly. So I'm going to write the formula for rankings. So for long column, I'm writing P is equal to P. So it is clear. That is the crushing load is the critical load on the short column. Buckling load is the critical load on the long column. So according to Euler's, I am writing 1 by P is equal to 1 by P plus 1 by PC. So I'm writing here 1 by P is equal to, by taking the LCM, we can write here P plus PC divided by P into PC. Now from that equation, I am writing 1 by P is equal to, take the P is common, then I am writing here PC divided by P divided by, so P into PC. Then P both are cancelled. Then I am writing 1 by P is equal to, that is 1 by Rankins load is equal to, that is 1 plus PC divided by P divided by how much? PC. Then what is P value? P is equal to PC divided by 1 plus PC divided by P. I got my point or not? Or got my point? So here, what is PC value? PC is nothing but crushing load. So I'm writing here crushing stress is equal to crushing load by area. At the same time, bending stress is equal to bending load by area. So here I am writing crushing load is equal to, that implies PC is equal to sigma C into area. That is area of the cross area of the column. Or you got my point or not? Area of the column. Right, then I am writing here. So sigma P is also is equal to sigma B into area. Or you got it? Right. So I'm going to substitute those two values in that equation. This equation, PC is equal to sigma C into area divided by 1 plus sigma C into area divided by, according to Euler's formula, what is the Euler's load for standard column? According to Euler's, generally I am taking both ends are hinged here, so that I am going to write it here. Both ends are hinged here. Pi square into E divided by, so L by K all square. L by K whole square, or we can write here pi square E into I divided by L square. We can write like this also. Automatically A both are cancelled. I will give it how it is cancelled now. That is sigma C into A divided by 1 plus sigma C into A divided by, so pi square into E. To I means K square into I, K square into A divided by L square. So A both are cancelled. Then I am writing here P is equal to sigma C into area, that is capital A, that is area of cross section of the column, plus I am writing sigma C divided by pi square into E into L by K. So I am writing here, that is L square. Here we are getting by K, we are getting whole square. So this value is nothing but Rankins constant. So I'm writing A is nothing but Rankins constant. Rankins constant, that is equal to sigma C divided by pi square into E. Then I am writing the formula, or sometimes we can take alpha also, no problem. In some textbook they written that the term is written as alpha also. So I'm writing Rankins load is equal to, that is sigma C divided by 1 plus A into L by K ratio whole square. So this is the formula for Rankins for both long and short columns. Or you got my point or not? Right? So in this way, we can calculate what is the critical load, what is the maximum load on a column when the column is subject to axial load. I got my point or not? So we are using different types of materials. We are using different types of materials. So for those materials having L by K ratio and A is also there. Here I'm going to give it some one or two values of Rankins constant. So here I'm writing for wrought iron. For wrought iron, Wi, that is nothing but wrought iron material, which is used to make a column. That A value is nothing but, so I'm giving the A values, Rankins constant values for different materials. That is 1 by 9,000, 1 by 9,000. For cast iron, so that A value is nothing but 1 by 1600. This is the A value, Rankins constant, A value, right? And one is mild steel. So mild steel, so the value is 1 by 7,500. That is the value. And last one is timber, strong timber. If you take timber, which is strong one, that is 1 by 750 is the A. These are the some values of Rankins constant for different materials. So I got my point or not? Right? Right. So please take care about the formula, this formula, then automatically we can calculate it here now. Okay, right. So this is the way of calculation of critical load by using Euler's formula and Rankins formula. Now I'm going to give some problems on Euler's and some problems on Rankins formula, how to solve problems on columns in gate point of view also. Right. So here, first of all, I'm going to give it to you. So how to calculate the uh, critical load according to Euler's formula. According to Euler's formula. So now see this one, the question number one here I'm writing. Question number one. A mild steel tube 4 meters long. This is a tube which is this is a mild steel tube which is having 4 meters of long. This is 4 meters long. This is made of mild steel. My internal diameter is 30 mm. This is nothing but it is if you see in this top view, it is having this is a tube. I'm going to draw like this. So this is the internal diameter and this is the external diameter. And the capital D is the external diameter. Capital D is given, sorry, the internal diameter is given small d. Small d is equal to 4 mm. So sorry, small d is equal to 30 mm is given. And the thickness is given. So this is the tube. And thickness is given, that is T is equal to 4 mm. T is equal to 4 mm. Usual sex, both ends are hinged. So these ends are hinged here. So this is a standard column according to Euler's. Both ends are hinged. So here he is asking what is the collapsing load? Collapsing load or critical load or buckling load, all are same. So here he is asking the question, find the collapsing load. Find the collapsing load. So take E is equal to, for mild steel, all of you know that. So 2.1 into 10 to the power of 5 Newton per mm square is given here. Generally, we are taking 2 into 10 to the power of 5 Newton per mm square for mild steel. That is for young modulus. Now, how to calculate the crippling load here, or critical load here, or collapsing load here? So, in this case, it is both ends are hinged. I already told you what are the formula for Euler's critical load according to Euler's theorem of column. That is, I'm writing here collapsing load or critical load or crippling load is equal to PE is equal to, that is a pi square into I divided by how much L square. How much here? L square. So here all are given, but here I am saying very simply. So what is the I value here? So I value. So I value for hollow cylindrical section. So I value is always equal to pi by 64 capital D power 4 minus small d power 4. This is the formula for hollow circular section for ice for I. That is moment of inertia for hollow cross section. So how to calculate this one now? So here this is thickness is given on both sides. Thickness is 4 mm, 4 mm. Then what is the external diameter? External diameter is equal to small diameter plus two times of thickness. That is how much here? That is this one is 4 plus 4. That is a d plus 2 times of 4 here. That is d is 30 plus 8. That is equal to 38 mm is the outer diameter. Why? Because when this is thickness is given. So internal diameter is 30 mm plus 4 mm plus 4 mm. Then we are getting the 38 mm is the external diameter. So here, then I'm going to substitute here. That is pi by 64 divided by into 38 whole power 4 minus internal diameter is nothing but 30 power 4. Then if you take that value, I got the value of I is equal to 92593 mm power 4. This is the value of I. Now I'm going to substitute in that formula. Then I'm writing here P is equal to pi square into E. E is nothing but 2.1 into 10 to the power of 5 into I value is 92593 divided by L square. L square is nothing but 4. You can convert into mm. That is 4 into 1000. So here is meters is given. I'm converting in terms of millimeters. Why? Because all terms are contains in terms of mm. So that I'm going to divide by 4000 whole square. Then I'm getting the P values. Then I'm getting the P values 8108 newtons. So this is the value of critical load on a column. Both ends are hinged according to Euler's theorem of column. So this is for a hollow circular cylindrical body or column. Okay, right. So this is the one problem. So this type of problems are given in GATE examination. So I'm giving the models. What are the models are we are going to have? So if you follow the models, then we can solve any problem in GATE examinations. Correct. And I'm going to give the next problem also. Right. In the second problem, in the second problem, a structure is given 2.5 meters long and 60 mm in diameter. So this is the structure is given. How much long is given here? 2.5 meters long. So this length of the column is given 2.5 meters long. And diameter is given, that is phi is given 60 mm. Phi is given 60 mm. One end of the struct is fixed. So this is one is fixed end. This one is fixed end. Other one is nothing but hinged end. Other one is nothing but hinged end. Find the safe compressive load. So he is asking find the safe compressive load. That is, he is asking what is PC, or we can write what is safe load. That is, I am writing here PS, safe load. It is not critical load. He is asking what is the safe load. If you know the critical load, automatically we can find the safe load also. Euler's formula, according to Euler's formula, take the factor of safety is given. So we have to calculate safe load, and factor of safety is given. That is, factor of safety of the material is given 3.5, and IE value is also given for the material, that is mild steel 2.5 into the power of 5 on Newton per mm square. So this is the question is given like this. So one end is fixed, other end is free. One end is fixed, other end is free. Then this length of the column is 2.5 and diameter is 60 mm. So here finding the safe load. So first of all, according to Euler's, according to factor of safety, that is always equal to, that is maximum load, that is P maximum divided by P safe, maximum load by safe load. It is also named as critical load. It is also named as Euler's load divided by PS. It is also named as maximum load. According to Euler's, it is named as critical load. It is also named as maximum load. I got it my point or not? Right. So here, so here, first of all, I want to find the what is the critical load. After that, I'm going to find the safe load. So what is the safe load here? So safe load is equal to critical load divided by factor of safety. So then I'm getting the safe load here. So what is the critical load here? That is P is equal to, that is P is equal to pi square into E into I divided by L square into 2 times. That is the value of one end is fixed, other end is hinged condition. That is the value of critical load according to Euler's for this condition of end conditions of the column. Then I am writing, so 2 into pi square into E is nothing but 2.10 to the power of 5 into I. I is nothing but pi by 64 times of d power 4. That is 60 power 4 divided by L square. L square is nothing but 2.5 into 1000 whole square. So this is the value of P. Then I got that value is P value. I got that P value 421820. 421820 newtons. That is the value of Euler's load or critical load. This is a maximum load, but he is asking what is the safe load here. What is the safe load here? So safe load is equal to maximum load is nothing but 421 and 820 divided by factor of safety is nothing but 3.5. Then I'm getting so 120,520 newtons. It is divided by 1000. 120.520 kilonewtons is the safe load which can be applied on the column. One end is hinged and one end is fixed. So that is the safe load. So I hope you understood that one. So in this way, we can apply, we can solve any problem. So like this. So in this chapter, so only problems are based on formula. So take the end conditions of the column and apply the formula, and take the known values and take the unknown values and find the unknown values here. Right. So this is the number 2. So I'm going to give one by one problems on this column. Abstract. All right. Here, I'm going to give it to you one more question here, question number 3. So listen carefully here. A solid circular compression member 50 m diameter. So this is a solid circular member which is having a diameter of 50 mm, 50 mm, which is under compression, which is under compression in diameter is replaced by a hollow circular section. So I'm going to replace it by this one by a hollow circular section. This is the hollow circular section. This is the hollow circular section. This is a solid section. It is also subject to a compressive load lines. Find the size of the hollow section if the internal diameter is 6 times of the external diameter. So this is the internal diameter small d, that is always equal to 0.6 times of capital D. That is the given data. Or we can write, so we can write anyway, or you got my point or not. So he is asking find the size of the hollow section. Question is given, find the size of hollow section. Size of hollow section means we have to find the small d value, we have to find the capital D value. So here length are same. The length are same. Yeah, you can take length are same. Diameter is given is 50 mm here for solid shape, and a hollow we have to find it. So how to solve this problem now here? How to solve this problem now here? So a solid circular member is replaced by a hollow circular section of same material. So here is material is also same. Here is also material is also same. When the material is also same, having same length and apply same compressive loads, then what about the I values, moment of inertia? So here moment of inertia are same here. That is so I'm going to write it here. That is I'm writing here small d is equal to 0.6 times of capital D here. So here I'm writing both columns to have same strength. Both columns are having same strength because both are having same materials and are having same length also. So here I am writing here I of solid divided by I of hollow. We can write it. Then I am writing here, so pi by 64 times of capital D equal to pi by 64 times of capital D power 4 minus small d power 4, right? Pi by 4 both are cancelled. So here is 50 power 4 is equal to capital D power 4 minus 0.6 times of capital D power 4. So 50 power 4, capital D power 4 is the common, then 1 minus 0.6 whole power 4. Then D power 4 is equal to 50 power 4 divided by 1 minus 0.6 whole power 4. Then if you solve it, you get the required value of D1 and D2. I will give it to you. So how much we got it? So 51 minus 0.6 whole power 4 and divided by answer. Then we are getting that value into 50 power 4. That is power of 1 power divided by 4. I am getting here 51 point. Capital D is equal to 51.765 mm. That is the value of capital D. How to find the small d here? Into we can write 0.6, then 31.059. So small d is equal to 0.059 mm is the internal diameter, and the capital D is equal to 51.765 mm is the external diameter. So these are the uh, dimensions of the column, which is a hollow circular column, which is given in this problem. So this is the way of calculation of size of the column. Right. So one more question I want to give it to you. So see this one. So this is a circular column. That is question number 4. I want to give it to you. So listen carefully. Question number 4. This is a circular column. This is a circular column. Both ends are hinged. Is according to your Euler's. Both ends are hinged here, which is having a length of L here. That is equal to L here, and which is subject to a compressive load of P. That is equal to P is equal to P. It is passes through its axis. It is also named as axial load. The diameter is given as capital D. So the question is given if the diameter is reduced by 20%. Question is given if dia is reduced by 20%, then what is the percentage of reducing Euler's load? Then what is the percentage of reducing Euler's load? If D is reduced by 20%, what is the percentage of reducing Euler's load? So actually we are calculating the critical load, but here I am asking what is the value of percentage of reduced in Euler's load when the diameter is reduced by 20 meters. Automatically the Euler's load will reduce. So maybe the diameter will reduce. So I want to find how much we can reduce Euler's load. So here, when both ends are hinged here generally, so P is equal to pi square into E into I divided by L square. Are you got it? So here is pi is constant, E is constant, L is constant. When diameter is D, when diameter is 20% is reduced, so the material is same. So L is also same. So these three terms are same now. So P is directly proportional to how much I can write it. So I am writing here, so percentage of reduced Earth's load is equal to, so PE1 minus PE2 divided by PE1 into 100. So this is the reduce in percentage of reducing Earth's load. But P is directly proportional to how much I value. P is directly proportional to which one? I value. So what is I value here? So I is equal to how much for a circular section? Pi by 64 into a d power 4. So in case of, so in all cases, so I is also directly proportional to d power 4. So I am writing here that is I1 minus I2 divided by I1 into 100, but I is also directly proportional to d power 4 minus 0.8 times of d power 4 divided by d power 4 into 100. So d power 4 all are get cancelled. Then I am getting here 1 minus 0.8 whole power 4. Approximately I am getting here 0.5904 into 100 into 100. So I'm getting approximately 59%. So approximately I'm getting here 59%. Right. Now I'm going to give another problem, so please take care about that one also. It is also right. So this is the problem. So you have to take it. So that is a problem number 5 here. Now in this question, find the shortest length L for pin ended steel column. So now we are going to find. So both ends are hinged column is given. Both ends are hinged column is given. We have to find what is the length of the column. Cross section is given. Area of cross section is given 60 mm into 100 mm. So take ES of this Young modulus of steel is 2 into 10 power of 5 Newton per mm square is given. And a critical load limit is given, that is PC or PE is given. Critical load is given, that is equal to 250 Newton per mm square. So here, so we can directly calculate what is the length of the column is required. So here I am writing. So here we have to remember only formula. If you remember the formula, we can calculate very easily. Or you got my point or not? So here area of cross section is given. So this is the column. This is the column is given. So one end is both ends are hinged here. Both ends are hinged here. Okay. Now, so here I am writing what is the stress value here. When the load is acting on it, then there must be a stress will develop here. So limit of stress reaches to up to this which value 250 mm. So P is equal to, that is P by area here, automatically 250 Newton per mm square here. That is a maximum stress. We are getting it. So here I am writing, first of all, according to Euler's critical load, so both ends are hinged, P is equal to pi square into E into I divided by how much? L square. L square. If we divide by both sides by area, so I'm going to divide on both sides by area. Then I'm writing here this one is nothing but 250 is equal to pi square into E into I divided by area into L square. Area into how much? L square. Or you got my point? Then I want to find L square here. So I'm writing here L square is equal to pi square into E into I divided by area into 250. Area into how much? 250. Then here, what is the I value here? I value is nothing but BD cube. I value is nothing but BD cube. So this is nothing but 100 mm and this one is nothing but 60 mm. So I'm writing here I value is equal to BD cube by 12. B is nothing but 100, D is nothing but 60, all power 3 divided by 12. I get my point or not? Right. So then I'm going to substitute here. So pi square, that is pi square into E value. What is the E value here? That is 2 into 10 power of 5 into I value is nothing but 100 into 60 power 3 divided by 12. Total divided by area is 60 mm into 100 mm into 250 mm. So if you put the square root for the center value, then we are getting the required value is nothing but L is equal to 1539 mm. So this is the value of length of the column is required. I got my point or not? Length of the column is required. So this is the another model. So in the previous cases, we have to find the what is the critical load, but here is we have to find the length and safe load and critical load. 3 points is clear. Critical load, safe load, and the length of the column is clear, and the diameter is reduced by 20%. Then what is the reduced Needles load? That is the four models is given. And the fifth one is and next one. I want to give it to you. So please take care about that one. So this is the column is given. Another question is given like this. A column is given which is made of a circular section of 5 meters long. So length is given 5 meters, which is in a circular column, solid circular column, which is both ends are hinged. Both ends are hinged. It is a circular column. Both ends are hinged. The length is 5 meters. The same bar, when freely supported gives a midspan deflection of 10 mm under a load of 80 newtons at the free center. For example, if you take this column, both ends are hinged here. So this is the hinged one. This is also a hinged one. Actually, if you apply this one like this, then automatically it bends like this. So if the same column is simply supported like this, simply support means we can put like this. This is both ends are hinged column. So if we simply support on the supports and and having a deflection automatically, if you apply and having a deflection of like this under a load of 18 newtons. The deflection is also is given. This deflection is nothing but 10 mm. Deflection is given 10 mm. So this is the same column. Both ends are hinged, freely supported on the supports, and a load of 18 newtons acts at the center, which is having the same length of 5 meters, which deflects a distance of 10 mm. Here is asking calculate the critical load here. Critical load here. So how to calculate critical load? So when both ends are hinged here, critical load P is equal to pi square into E into I divided by how much? L square. So here E is not given. So I can find it. So that is which is in the circular section. This is circular section, circular solid section. So I can find the I value pi by 64 into t power 4. Okay, right. So here I want to find the what is the critical load here. So I want to find pi is known and L is known. So I want to find the EI value. So how to find the EI value? By taking the deflection here. Deflection is here is nothing but delta. So this is the column. Both ends are simply supported and which is subject to a point load at its min end. When this column is subjected to a point load, which is a simply support beam, the deflection formula, I will give you how to calculate the deflection for simply supported. Remember that is WL power 3 divided by 48 times of EI. So this is the formula for deflection of a beam or column when the load is exactly acting at the center, which is simply supported, Now from this one, I want to find the EI value. So EI is equal to how much? WL power 3 divided by 48 times of delta. 48 times of delta. So then I'm getting here 125 divided by 6 into 10 to the power of 9 Newton per mm square is the value. Then I'm going to substitute this formula in this one. Then P is equal to so pi square into E value, E into I value is known, then 125 by 6 into 10 to the power of 9 divided by L square. L square is nothing but 5000 whole square. Why? Because 5 meters is given is length. I want to convert in millimeters, 5 into 1000. Then we are getting the value of, okay, right. So this is the value of critical load. So on this count, then I've got the value of 8225 newtons. So this is the value of this one. Okay, I hope you understood this one. Right. So here I want to give one more problem. Please take care about this one. A steel bar of rectangular section, the rectangular cross section is given. So that is 30 mm into 40 mm. 30 mm into 40 mm in rectangular section is pinned at each end is subject to an axial compression. So both ends are hinged. Both ends are hinged, right? Both ends are hinged. A bar of length of 1.75. Length is given 1.75 meters. So the question is given, determine the buckling load. Determine the buckling load first of all, and at the same time find the L by K ratio, that is slenderness ratio. Buckling load P and find the L by K ratio, right? Now, first of all, I'm going to write it here. So what is the buckling load? P is equal to, both ends are hinged, pi square E into I divided by how much? L square. So pi square into E value. So E value is given also. That is E is equal to 2 into 10 power of 5 Newton per m square. It is mild steel. So we can write here 2 into 10 to the power of 5 into I value. It is circular scar rectangular section. I value is nothing but BD cube. B is nothing but 40. Depth is nothing but 40. 30. So we are writing here 40 into 30 power 3 divided by 12 divided by L square. L square is nothing but 7.5 into 100 whole square. So if you solve this one, automatically we are getting the value of, so I'm getting the value 58,009 newtons. If you divide by 1000, we are getting approximately 58 kilonewtons. I want to find the bending stress here. Bending stress is equal to P by how much? Area. So P is 58,009 divided by, so 30 into 40. So mm. Then automatically we are getting the value of 48.34 Newton per mm square. So this is the value of stress. And according to Euler, so sigma b is equal to, so pi square E into E divided by how much? L by K whole square. This is the formula for bending stress according to Euler. So I want to find the L by K ratio. That implies L by K whole square is equal to pi square into E into divided by sigma b. If you take the square here, I'm putting the square root. Then I'm getting the value of 99.34. So this is the value of L by K ratio. This is also named as limitation of Euler's theorem of column, or limitation of Euler's theorem of column. Or got my point or not? Right. So this is the way of applying the Euler's formula. So to calculate any value. Or got my point or not? Right. And one more question I will give it to you. After that, I will give the explanation about the Rankins formula also. Please take care about this one now. Another question. Determine the ratio of buckling loads of two circular columns. One hollow, other one is solid. So this one is hollow column and this one is solid column. This one is solid column. Both columns are made of same material. So for same material, both are made of same material and having same length and having same length, comma area of cross section and the end conditions and the end conditions. The internal diameter of the hollow column is half of its external diameter. So this is a small d is equal to half of the external diameter. That is also is equal to 0.5 times of capital D. So this is given. I got my point. So this diameter is I am going to take it as capital D. I got it. Right. So please take care about that one now. So this one is we are taking here. This internal diameter is D2. This external diameter is I am taking as D1. So here is D2 is equal to 0.5 times of D1. So take that conditions here. This one is nothing but D. Okay. So he is asking what is the ratio between the Euler's loads. So here is Euler's load for hollow section and this is the Euler's load for solid section. So I'm going to calculate what is the Euler's load for hollow and Euler's load for solid section. Right, this is also very simple. They will ask any type of question in GATE examination. So here is for same material, for same length, area of cross section and the conditions are same. So area of cross section is same here. So for this area of cross section of hollow, pi by 4 into, so that is d1 square minus d2 square is equal to pi by 4 into how much d square. Pi by 4 both are cancelled. So d1 square minus d 0.5 into d1 whole square is equal to d square. Then d1 square is common. 1 minus 0.5 whole square is equal to d square. So I'm writing here d1 square divided by d square is equal to 1 by 1 minus 0.5 whole square is equal to I'm writing 4.3, 4 by 3. That is the condition. I got my point or not? So now here buckling load for hollow divided by buckling load for solid. So automatically if the both conditions are same here, P equal to, we are writing here, P is equal to pi square into E into I divided by how much L square. So this length is same, so entirely common. So P is directly proportional to how much I value. So here I am writing here, so P of hollow divided by P of solid is equal to, directly we can write IH divided by IS. What is IH here now? D1 power 4. Generally we can write here pi by 64 times of D1 power 4 minus pi by 64 times of D2 power 4 divided by pi by 64 times of D power 4. So pi by 64 all are cancelled. Then automatically we can substitute all the values. Then I'm getting the value PEH divided by, so PES solid is equal to 5 by 3. So this is the ratio we are getting. Or you got it? Right. So this is the way of calculation of way of calculation of Euler's load and different types of problems which is based on Euler's load for different end conditions of the column. Okay, right. So now I'm going to give it you what are the problems on rankings. So I'll give one or two problems on Rankins formula. So Rankins formula is also very important in solving problems. So that is suitable for both short column and long column. So this is a question is given Rankins formula. The problems on Rankins formula, I will give it to you one or two problems. So a mild steel column is given. A mild steel a column is mild steel column is given having a cross section is given 25 mm into 25 mm. It is in square cross section, which is can be used as a compression member. Which one end is fixed, other end is free. Which one end is fixed, other end is hinged is given. Carries a load of, so P is given, that is equal to 35 kilonewtons is given. Factor of safety is also given. Factor of safety is also given, that is 4. And the Rankins constant A is also given 1 by 7500. And the compressive stress is also is given sigma C, that is 320 Newton per m square. These are the data which is given on this column. These are the data which is given on this column. One end is fixed, other end is free. So here we are going to calculate what is the critical load. So what is the formula for critical load here? What is the formula for critical load here? We know that the critical load formula is simply, that is P or Rankins load is equal to, so that is sigma C into area divided by 1 plus alpha into, or we can write A into L by K whole square. This is the value. Or you got it, my point? Right. So here, what is sigma C value? Sigma C, we know that. What is sigma C value? 320. That is 320 into area is nothing but 625. That is 25 into 25. Automatically, we can write 625 divided by 1 plus area 1 by 7500 into L square. What is the length? Length is not given. L square divided by 52.08 is the L by K ratio. That is, you are writing, I am writing here L by K ratio, L by K whole square. So here, how to calculate what the question is given on of the carrying load. Find the greatest length. Length we have to find it. Find the greatest length of the column. So L we are going to find it. How to calculate K here? K is equal to I by A. K is equal to how much? I by A. That is under square root. I we know that that is the square section, right? That is 24 power 4, 25 power 4 divided by 12. Under square root of area is nothing but 25 into 25. Then we are getting the K value. So that is 52.08. That is mm square. Right. If you substitute in that formula, if you substitute in that formula, you will get the L value. If you substitute in that formula, then L is equal to, I got that value. L is equal to 5408.9 mm. This is the value. right? Here, in this way, we can substitute for any case. So direct write the formula and substitute all the terms and we will get the required values. Right. Now here, so these are the formulas. So P is equal to pi square into E into I divided by L square and P Rankins load is equal to, that is P is equal to sigma C into area divided by 1 plus A into L by K whole square. These are the values of critical loads according to Euler's and according to Rankins formula. So when these two formulas are subject to axial compressive load. So to find the critical load, these are the formulas we can use to find the critical load when the column is subjected to axial load. If the column is subject to eccentric load, what happen here? If the column is subject to eccentric load, what happen? See this one. So next one I'm going to give it to you. When the column is subject to eccentric load. So here I'm writing here case number 2, column with eccentric load. Column with eccentric load. So eccentric load means, for example, if you take this is the column, example, this is the column, this is the axis of the column. I'm going to apply a force like this. This force is nothing but P, and the distance between this axis and this P is nothing but E. E is called eccentricity of the column. Eccentricity of the column. Are you got my point or not? So if you apply the eccentric load, the column having two stresses, that is one is direct stress, one is direct stress. It is also named as compressive stress, that is sigma C, that is also is equal to P by A, that is PC by A. We can write it. And second one is nothing but bending load. It is bending stress. What is the bending stress here? So bending stress sigma B. What is the bending stress here? We know that when this column is under bending, we know that M by I is equal to sigma B by Y is equal to how much? E by R. E by R here. Automatically, if it is bending like this, we are writing sigma B is equal to M into Y divided by I value. I'm writing. Forgot my point or not? So here the M is nothing but how much? M is nothing but bending moment. Bending moment is nothing but P. Bending moment with respect to center is nothing but M is equal to how much? P into E. That is bending moment. So Y is nothing but deflection of the column. So for example, when the column is deflected like this, this is the deflection. That is Y. I got my point or not? So I'm writing here. So this is Y, this is Y, this is I value. I value is always K is equal to how much? I divided by A under square root. Then that implies I is equal to how much? Is K square into area. That is very simple according to the radius of gyration. So here maximum compressive stress is equal to, what is the maximum compressive stress? So maximum load is equal to P maximum is equal to, that is crushing stress, maximum stress I am writing here. That is sigma maximum is equal to sigma under crushing plus sigma B. That is we are writing sigma is nothing but P, sigma C is P by A plus in place of M I am writing here P into E, that is P into E into Y divided by I value. So I am writing P into E divided by I into Y value. Or you got my point or not? So here We can write here in place of phi, we are writing a k square into area. So sigma maximum is equal to, we are writing P by A plus P into E into Y divided by area into K square. So in this one, P by A is common. So maximum is equal to P by A is common 1 plus E into Y divided by K square. So this is the formula for maximum stress in the column when the column is subject to eccentric load. Column is subject to eccentric load. So what is the safe load here? So here we are going to find the what is the safe load. This is the formula according to Rankins method. What is the Rankins method here? Rankins method is equal to P is equal to, yeah, we know the stress is equal to the compressive stress plus bending stress. So we are writing here. This is the analysis with respect to Rankins. This analysis is total stress is equal to compressive stress plus bending stress. Now here, what is the safe stress? What is the safe stress on the column for eccentricity E is given by. So for example, if you apply this load at this point, that is axial load. So if you apply the load away from this center point, that is nothing but eccentric load. So we are going to find at what distance of E we are going to apply load P without any bending, without any deflection, without any bending. That is nothing but eccentricity. That is nothing but safe load without any bending. That is safe eccentric load without any bending. Or you got my point or not? So I am writing what is the safe load without bending. That is, I'm going to write it here. What is the safe load here? So please take care of that formula. So we can use the formula only. So here I'm going to write it here. It's again. So please take care about this one now. So maximum stress according to rankings sigma maximum is equal to P by A into 1 plus E into Y divided by K square. So according to Euler's also we can find it. So now here, what is the safe load on the column? Safe load with E, that is with eccentricity E. Safe load with E, that is P is equal to, this is for according to Rankin's formula, that is F. F is, what is F value? F value is nothing but directive stress value. So F into A divided by or safe stress, we can write here into A divided by 1 plus E into YC divided by K square. So this is the formula for safe load. If the effect of buckling is also included, then the safe eccentric load is buckling is also included here. Then we can tell this one. If buckling is also included, if buckling is also included, so this is for only crushing, right? So if buckling is also introduced here, then the formula for safe load is nothing but so sigma s into area divided by 1 plus e into yc divided by k square into 1 plus alpha into L square by K square. So this is the formula for the safe eccentric load. The safe eccentric load without buckling. So this is for both with buckling. So this is for maximum stress according to Rankin's formula. So here, according to Euler's also, we can find the what is the crushing safe load on the column and what is the maximum stress in the column also according to Euler's. So I will give it to you. So what is the value of Euler's? It is also named as secant formula. It is also named as Perry's formula also. Okay, right. I'm going to give it to you. So what is Perry's formula? So we can apply according to Euler's method. We can find the critical load on a column, that is a critical eccentric load on a column. We can find it by using the Perry's formula or secant formula. Now, you got my point or not? Secant formula, we can use it. Uh, After that, did the small modifications, we are going to use the Perry's formula. So, this, according to secant formula, so according to Euler's, the maximum stress is equal to P by A plus P into E into secant L into square root of P divided by E into I divided by Z value. What is Z value? Section modulus of this one. Section modulus of the cross section. Here is for both ends of the column has been hinged. It is shown maximum bending moment is if the both ends are hinged. That is stand column. Both ends are hinged. Both ends are hinged here. Automatically we can write M value, bending moment value. Here actually this one is nothing but M by Z. That is M by Z value. This total is M value. So M by Z is nothing but section modulus. M is equal to how much here? Then M is equal to, so P into E into secant L by 2 into square root of P divided by E into I. So this is the value of bending moment. Okay, this is according to which one now? Euler's maximum stress formula. So here, this is the here Professor Perry's formula also we can use it. This formula which is found useful for case where we have to determine the safe load that can be applied on a column at a given eccentric load. So Perry's formula is also used to calculate the critical load when the column is subject to eccentric load. Or you got my point or not? What is Perry's formula here? Or you got my point or not? So here I am writing here according to Perry's formula. This is secant formula. So simple modification of secant formula is nothing but Perry's formula. So here I am writing here Perry's formula. Perry's formula. According to Perry's formula, I'm not given the derivation part, so we can use this formula that is P maximum, that is stress maximum, divided by P naught minus 1 into 1 minus P naught divided by PE is equal to 1.2 times of 1.2 into E into YC divided by K square. So this is the formula. So here is also we can write here sigma maximum by sigma naught minus 1 into 1 minus sigma naught by sigma E. That is, or you got my point or not? Sigma maximum permissible compressive stress. P naught maximum, P maximum is the maximum permissible compressive stress. I can write like this also. You can write like sigma maximum divided by sigma naught bending. Here is sigma B, right? Minus 1 into 1 minus sigma B divided by sigma E, yield stress value. You got my point or not? So here is, sorry, mistake now. So here is one. I'm giving to you. So P maximum is nothing but maximum compressible stress, maximum permissible compressive stress. And here is P naught is also there. That is P naught stress due to direct load, stress due to direct load. And here sigma B bending, stress due to bending. You got my point or not? Right. So these are the values here. This is the formula for Perry. So here is formula we can use it to calculate the what is the maximum stress or what is the critical load or eccentricity E value for a column which is subject to eccentric load here. Okay, right. So in the gate point of view, maximum they are asking questions on. So the columns are subject to eccentric load and axial load according to your Ehlers and according to Rankin's formula. Okay, so be careful about the columns and structs. So the one more thing is when the column is subject to axial load and eccentric load is clear. So careful about this one. So this is about columns and structs here. So here, so up to this one is columns and structs is over. So you have to remember the formula and take the what are the conditions are given. That is what are the end conditions of the column is given and what the question is given. So read carefully and apply the formula and substitute the given values and automatically we can get the required value. Okay, so take care about those formulae and problems. That is enough for gate point of view. So now I will start with another new chapter that is nothing but strain energy. That is nothing but strain energy. That is also very, very important in gate examination. Strain energy, springs and deflection of beams and theories of failures are also very important. So here, I'm going to explain about strain energy now. So please take care about this one, strain energy. So when we get this strain here, when we get this strain in a material, if you apply any external force, then we are getting strain in a material. So here what I am saying here, so when a body is under strain, for example, I am taking a bar here, I am taking a bar here, this bar is having a length here, one side is fixed here, other end is free here. It is also vertical cantilever beam. It is a hang like this. So this is the length of the bar L. And here I'm going to apply some load here. That load is equal to how much P, or we can write W also, P. So what happens here, if you apply some external force on a bar, which is having a length of L and area of cross section is A, then automatically this bar undergoes some deformation. If you increase the load gradually, and the deformation is also occurs in the material and it will deform up to this one. And this is the load here, and this deformation is always equal to how much delta L. So how to find this deformation here, delta L? The deformation delta L can be found by Hooke's law. So when this material is said to be elastic material, then delta L is equal to how much? PL by A. PL by A. Now see this one. If you apply some external force at the free end of the bar, and if you increase the load gradually, it undergoes some deformation. If you release the load, automatically it comes back to original position. Then it is said to be elastic material. Otherwise, it is not elastic material. If it is elastic material, we can follow the Hooke's law. Then we can use this formula. We can use this formula. Or you got my point or not? So here, when the material is said to be under deformation, it is under strain. So what I am saying here, strain energy. That means when the body is under strain, it stores some energy. When the body is under strain, it stores some energy. That energy is always named as strain energy. So this energy may be different forms. So in our nature, energy are different forms. One is said to be potential energy, kinetic energy, work energy, heat energy, nuclear energy, chemical energy, flow energy. There are wind energy, fluid energy. There are different types of energies are there. But here, uh, if you apply the load, automatically this bar undergoes some expansion or deformation up to a certain distance. Then this bar moves from this point to this point, so that this bar is said to be under strain. So during this strain, it undergoes a deformation. During the deformation, this force done some work on this bar. This force done some work on this bar. So work done by the force on the bar. So I'm writing here work done by the force on the bar is equal to how much now? Work done is equal to force into displacement. So I'm writing here force into displacement. Now, what is the work here? So, work is form of energy. So, this is the energy which is stored in the material, which is under deformation. It is also named as work done or work energy. It is also named as strain energy. Strain energy, which is also stored in this material in the form of work energy. In the form of work energy. So, strain energy is equal to work energy here. Here is in the form of work energy. But in some forms, there must be in potential energy, there must be in kinetic energy also. So now here strain energy is equal to work energy. So here we are applying the force. We are increasing the force gradually so that this deformation is also goes on increases. All of you know very well. So here strain energy is equal to work energy. Work is equal to how much? Force into displacement. Force into displacement is nothing but delta in this case. I got my point or not? Then what I am saying here, that is WU is equal to stage is equal to force is nothing but P, delta L is nothing but PL by A according to your Hooke's law. All of you know it. So here P is not constant. If you deform this material from this point to this point, this point to this point, this point to this point, we have to increase the force gradually. So it is named as gradually increased force or gradually applied load on a member which undergoes some deformation. So here the P is not constant. So I am taking the average force. I am taking average force. So force is here is force is always average force. Why? Because point to point force is varies. So here take average force. So I am writing here strain energy is equal to I am writing half into that is P into P by A into L by E. But what is P by A? Stress value. I am writing half into P into stress into L by E value. But what is P here? We know that stress is equal to P by A. But P is equal to stress into area. We can write it. Or you got my point? Stress into area. Then automatically I'm writing here stress, that is strain energy is equal to half into, in place of P I'm writing sigma into A into sigma by E into L divided by how much? Sorry, divided by E. But sigma by E is nothing but strain. According to which formula? Hooke's law. Stress is directly proportional to strain. If you remove the proportionality, stress is equal to n modulus into strain. So strain is equal to sigma by E value. You got my point or not? So that I'm writing here I'm writing here U is equal to half into stress into this one is strain into area into length. Then I'm writing strain is equal to half into stress into strain into what is this value? This value is nothing but volume. So this is the value of strain energy under gradually applied load, or it is also named as under static load. Under static load. So this is strain under static load or gradually apply load. Or you got my point or not? So this can be rewrite like this also. So please take care about this formula. So we can write strain energy is equal to half into stress into strain into volume. At the same time, we can write like this also. So here I'm writing strain energy is equal to half into stress into strain into volume. Otherwise, we can write half into stress into strain is stress by Young modulus into volume. I'm writing sigma square by 2E into volume. So this is also the formula of strain energy under a gradually applied load or under a static load. If you take this is for volume is per unit volume, that is strain energy per unit volume is equal to that is equal to sigma square by how much? 2E. It is also named as modulus of resilience. It is also named as modulus of resilience. Modulus of resilience. So this is the calculation of strain energy in a gradually applied load. So at the same time, I want to calculate what is the strain energy under different cases. So in our strength of material, we are having different cases here. So what is the strain energy under tension, under compression? I'll give it to you one by one. So please take it now. So there are different cases. I'm writing here strain energy under tension or compression or gradual applied load or static load is equal to sigma square by 2E into volume. This is the one. This is the first case. And the second case is nothing but under suddenly applied load. Applied load. And third one is impact load. And the fourth one is under shearing. And fifth one is under bending. And sixth one is under twisting. Suddenly applied load, gradual applied load, impact load, under shearing, under bending, under twisting, and last one is nothing but stage under three-dimensional, two-dimensional, and one-dimensional. So these are the different types of cases of strain energy. Strain energy under static load, strain energy suddenly applied load, impact load, under shearing, under bending, under twisting. Um, and in one dimensional, two dimensional, and three dimensional. These are the cases, and first case is very simple. So that is sigma square by 2e into volume. We can find it very easily. But in the case of suddenly applied load, I will give it to you. In the case of suddenly applied load, I will give it to you. So please listen carefully here. I'll give one by one. So here stage under suddenly applied load. Stage under a suddenly applied load. So here I am taking here, this is the bar. This as same as in the previous case. This is the bar. So here we are going to add some weight here suddenly. Then this weight is equal to how much P. Then automatically this bar will expand like this up to this one due to that suddenly applied load. So here load is not applied gradually here. So load is applied suddenly here so that this is the deformation of the material or elongation of the material delta L. So here strain energy is equal to general formula work energy. Work is equal to force into displacement. Force is nothing but P here, displacement is nothing but L. So here in the previous case, gradual applied load, we are taking average load. So here we are not taking average load, we are applying the load suddenly. So take that load. So take that load directly. So don't take the average load. So I'm going to remove the half here. Then I'm going to write here P same. So P into PL by how much? AE. Then I'm writing here sigma into area, and this one is nothing but sigma into L by E. Then sigma into sigma nothing but sigma square by E into how much? Area into length. That is equal to how much? Sigma square by E into volume. So this is the value of strain energy in suddenly applied load. Or got my point or not? So we can find the strain energy under impact load also. So what is the strain energy in impact load? So I'll give it to you also, right? So take care about this one also. Okay, right. I will give it to you. So listen carefully. What is the strain energy and impact load? This is for strain energy under gradual applied, suddenly applied load. This load is applied suddenly. The load is attached to the bar suddenly. Then the bar is on a deformation up to a delta L. Then the delta L can be calculated by using Hooke's law. Why? Because this material is elastic material. It follows Hooke's law. That is delta L is equal to PL by AE. Then automatically we can write sigma into A area. So P is equal to sigma into area, and P by A is nothing but sigma. That is L by E. Then we can write sigma square by E into area into V here. Area into length here. Then area into length is nothing but volume. Then U is equal to sigma square by E into volume. This is the strain energy for suddenly apply load. Now I'm going to give it to you. So what is the strain energy of impact load now? That is impact load. Impact load means it is not gradually apply load. It is not suddenly apply load. It is impact load. Impact load means the repeated loads. Now that is see this one. We are going to apply impact load. Strain energy under impact load. So this is the diagram. I'm going to take it. This is a negligible weight. A small plate is attached to the bottom of the bar. It is a negligible weight. So here I am taking the weight here, P, which is sliding on this bar, which is at a height of h from the bottom plate. bottom of this bar, that is H, and it can slides on this bar like this. It can move up and down if you release it. So if you release at a height of h, it can move from this point. This point goes to impact. After impact, so it will expand like this. This is nothing but impact load. It will expand like this. After impact, this load is also moves along with the plate. So this is nothing but impact load. So what is this one? This distance is moved by this plate is nothing but delta L. What the total distance moved by the load here? H plus delta L. Or you got my point or not? So this is the impact load. So we can maintain the load at a distance of h from the bottom of the bar and release at this height. If you release it at this height, automatically the load goes to impact this bottom of this bar. Then this bar undergoes some deformation. During the deformation, uh, it is under strain. So when this bar is set to be under strain, it has some energy. That energy is also named as strain energy. So here I am telling to you how to calculate this strain energy in this case. Okay. Right. So I will automatically we can write here strain energy is equal to how much work energy. So work energy is always equal to force into displacement. But the force is nothing but P here into displacement is nothing but H plus delta L. So this is the total displacement of the force. Then I'm writing here P into H plus delta L into P into delta H. P into delta. So I'm writing here U is equal to, I'm writing here P into H plus P into, so PL by A. So that is according to Hooke's law, delta L is equal to how much? PL by A. Then U is equal to how much? PH divided plus, we can write here P plus, we can write here PL by A nothing but sigma by A, sigma by A into L by E. We can write it. So this is the formula we can use to calculate what is the strain energy value in impact load. So we can convert into stresses also. So this is also after impact, it is also is equal to gradually apply load here. So we can write sigma square by 2E is equal to volume. So here I'm going to equate this one. That is sigma square by 2 times of E into volume. Volume is nothing but area into length after impact. That is PH plus P into sigma by A into L by E, or got my point or not. So I am taking the sigma square terms one side and sigma terms another side. Then we can take the factors of sigma. Then we can get the factors plus or minus. Then we can get the what is the maximum stress which is developed in the bar. So I'll give it to you tomorrow, the clear explanation of this strain energy. So up to this one, you have to remember, first of all, that is what is strain energy here? This is strain energy under impact load. This is strain energy under impact load. That is PH plus P into sigma by A into L by E. So, so tomorrow I will complete this strain energy and I'll give some problems which are given in GATE examination on strain energy. After that, I will start with the deflection of beam. That is very, very important chapter in GATE examination, deflection of beams. So this one is thank you to all of you and thank you very much to all of you. So tomorrow we will meet at the same time. So thank you very much.